Hi, this is Adam Baker from Affinity Energy. Here today talking about how to do controls for small solar plants, the qualified facilities or the QF type sites that are easy and quick to implement. Lots of independent power producers are building them all over the state of North Carolina and the extended area. And just wanted to share some experience I've had from my history in doing very large site controls, as well as how we've applied some of that to what we're doing on some smaller sites in actual applications today. So this is best practices for solar qualified facilities, or QFs, to play friendly on the grid. I'm going to talk a little bit about some of the recent experience we have with doing active power control, and I can talk also a little bit about how we're doing some power factor control on these very small sites and why it might be important. Affinity Energy is a systems integrator. We are highly focused on critical power applications and distributed generation. So this is really the core of our business. Personally, I've been working in the solar industry since 2010 on what started off as the biggest solar power plant in the United States, followed by two more even bigger solar power plants in the United States. So I've got quite a bit of experience in doing controls with solar power, and I really know how to make a site hum. So grid stiffness is an issue that has come up quite a bit in North Carolina and other parts of the country as well. There's a lot of concern that the more generation you have from these variable sources of energy like wind and solar, the more grid instability you're going to have. So there's a tiny bit of truth to the issue. If there were a large number of solar sites on the same distribution line and they were all to power up instantaneously, it would cause a little bit of a shock to the system. However, the sites are designed so that that shouldn't happen, and controls can make it so even if it were to happen, they would come online gradually and they'd go offline gradually, which would reduce or minimize the shock to the distribution system. So this concept that solar is bad for the grid, that you hear a lot on the news, it's actually fundamentally not true. And from the studies that we've been publishing through the years from my time with previous employers and through the NREL, we've got some real good data that shows that solar can actually be very helpful to the grid. So the issue of grid stiffness occurs based on design of energy flow from transmission lines through a substation and then out through a distribution feeder to neighborhoods and commercial buildings and all of the consumers of electricity. It was designed that way 100 years ago, and it wasn't designed with this concept of a source of energy existing down that line, that distribution feeder. So now where you've got what would be a voltage drop because of the current flowing through the distribution feeder, the utility would introduce a boosting transformer to bring the voltage back up where it had dropped sufficiently. Now when the solar site is introduced and the amount of current flowing from the substation is reduced, the voltage drop is reduced. So what might be a 1.1 kV voltage drop to 11.4 kV where the boosting transformer is, it would increase the voltage by 10%, bringing it back up to 12.5. Now the voltage at the substation side of that boosting transformer might be 12 or 12.1 kV because the current has dropped enough. And now when you're boosting that, it might be causing an overvoltage condition for the neighborhoods on the solar site side of that boosting transformer. So a good chunk of my time when I was working with First Solar, we had many sites that were being built in Southern California in IID, or the Imperial Irrigation District. This is the area east of the mountains in Southern California. So most of the people live west of the mountains, but there's a whole lot of wind and solar generation on the east side of the mountains, and there's a whole lot of farmland out there. It's a great area for generating power, but there aren't a whole lot of consumers of power in that area. So it all has to be transmitted through transmission lines west over towards the large population areas of San Diego and Los Angeles. So the problem is that the transmission lines leaving the IID area don't have enough capacity to take all of the energy when it's both very sunny and very windy. And therefore, some of those sites need to be curtailed to outputs lower than their design capacity or shut off altogether in order to limit the energy flow to the maximum amount the transmission system can handle. So for those generation facilities in the IID, when generation is low, at nighttime, the wind facilities will continue generating. There's no solar output, so there generally isn't issues with congestion on the transmission line. But in the day when all of the solar facilities are coming online and the wind's running, and congestion is causing a problem with the transmission lines, there are three things that can happen. Some of the sites will be left on. Wind sites typically do not get significantly curtailed. They don't run well at a lower output than what the wind is trying to push them for. The solar sites, some of them can be curtailed to a lower output. So you can take a 100 megawatt site, command it to 50 megawatts relatively easily if the site has a control system. Or if there's too much generation and the sites don't have the ability to be curtailed, then they're just cut off completely. Somebody will open the 52 breaker at the site, whether it's the customer or the transmission operator, and just take the entire facility offline. So when you have the ability to provide active power curtailment in your site, you're less likely to be curtailed offline and more likely to be commanded to just run at a slightly lower output or a significantly lower output than you would otherwise. But when you're in that condition, if the demand goes up or some transmission capacity becomes available, you're more dispatchable to increase the active power output from the site on short notice. So you're a more valuable generation asset to the transmission operator. So avoiding curtailment, obviously if you are the owner of a solar power site, what you're really most interested in is maximizing your output all of the time. You want to make as much money as you can, keeping the site running at maximum output. But as I said, if the transmission system or the distribution system has capacity issues, if you have the ability to vary your output, you may get lowered, but you're less likely to be tripped offline. As I mentioned, you have the ability to recover and bring the output back up on relatively short notice. So it's better for the utility to have you still running at a lower output than taken offline completely, where you might not be able to start back up quickly. So how do you avoid curtailment? First of all, have the ability to curtail in an analog manner, not just on or off, having the site be on or off, but having the ability for the site to be able to be adjusted anywhere between 100% output and 0% output. So going back to the Imperial Irrigation District, early, before most of the sites were implemented with control systems that allowed for curtailment, when there was an overgeneration situation, the sites without the ability to do active power curtailment would be shut off first. Then the gas plants would be turned down or shut off. And then the solar sites that had variable output, those were the ones that ended up being curtailed last. So the sites that had a lot of flexibility in what they could provide, those were the ones that are most valuable to the balancing authority. So those are the ones that tended to stay on the longest. So if we look at how this works in practice, we've got an output from a plant as measured by a power meter, which that number should correlate pretty closely with what the inverters themselves are reporting their output are. If we have a set point for the plant at 5 megawatts, the inverters are generally configured so that they can't go beyond 5 megawatts. They can only produce 5 megawatts of power coming out of the plant. When we change the plant set point from 5 to 4, what we actually do is we send an updated command to the inverters to not run at 100% output, but to run some level below that, maybe 80% output. And it'll actually be perhaps a little higher than 80%. So that we can compensate for losses, or if a cloud comes, we can actually turn up the inverters that are generating to compensate for that and do closed loop control. Or we can do open loop control, knowing how many inverters we have, what the target is, and command the inverters that are available so that we get the desired output, whether it's 5 megawatts, 4 megawatts, 3 megawatts, or any point in between. Then the control system, as it commands the inverters, doesn't just send a new command at the new value and allow the inverters to step down quickly. It'll ramp the command down over some period of time. Typically 10% of the plant capacity per minute is the standard. So if it were a 5 megawatt plant, it would ramp at a half a megawatt a minute. So if you command a 1 megawatt change, it'll take 2 minutes to get from the previous set point to the new set point. That's kind of typical for the large generation industry. You may want it to run faster or slower. It's that slow transition of set points that allows the grid to work well with the solar plants, or the solar plants to work well on the grid. So if you look at what has historically been done at these QF sites, I very rarely see a site that has a control system in it unless it's a requirement of the interconnection agreement. And that doesn't happen very often. So typically you've got a site, it's got a recloser that's controlled by the utility most of the time. And then you've got medium voltage coming into one or multiple transformers on the site, and then inverters that are just designed to run at whatever their Pmax, or their maximum power output, is configured for, so that you can achieve the output of the plant as designed. Most all of these sites have a monitoring system that will tell you what is going on inside the plant. So there is an infrastructure there, but no actual ability to do closed-loop real-time controls. It's simply the matter of adding a device that will send the commands to the inverters as a change to allow this control capability. So it's not a significant change in the infrastructure that's installed. It's a relatively low-cost adder, especially if you look at the overall project cost. It's a very small cost adder to have this capability. So the product that we've used whenever we've done control systems for these QF sites, and sometimes when we do control systems for the larger sites as well, is a product made by SEL or Schweitzer Labs. It's called an Artac. They're very often used in large sites as a RTU, or a data concentrator for those sites. So it's a product that's well known to industry, well accepted in industry, and it has the ability to do just about all of the types of control you can do with a PLC. It doesn't have all the interfaces that you would use in standard automation where a PLC would be appropriate, but from a functionality standpoint, it has all of the abilities to do ladder logic programming and function block programming and structured text programming like you would have in a PLC. So it's a data concentrator, but it can also be used as a plant controller at the same time. And as I said, we've used it successfully in several applications for qualified facilities as well as larger facilities. As far as capabilities, the Artac is very fast response, so it's PLC-like in its response time. We can do grid voltage control at a 250 millisecond closed-loop response time. So any of the interconnection agreements that I've seen in the United States that had very specific requirements for how fast the system had to respond to a command or a change in conditions, the Artac's capable of supporting any of those requirements. And then because it's also used often as an RTU or a data concentrator device, it has the ability to do GPS time synchronization and interface with external utilities. So it is the device that I would prefer to use if a customer wanted to interface with a transmission operator to do AGC, or automatic generation control, where the utility themselves would just send in real time a SCADA command for what the plant should do for an output. We wouldn't need manual controls or operators to go in and change a set point in order to have the system respond. It can be tied directly to the balancing authority to take the commands and adjust the plant output. So just a couple more points on the case for why to use an Artac. Some of the monitoring systems have some ability to do controls built into them, but the Artac itself, it already knows how to talk to everything that's going to be in the plant. It already knows how to talk to external devices. It's a lower cost device than many of the options that are provided by the monitoring companies to monitor the site. The Artac device itself there's a version of it that's available for less than $1,000. So it's an inexpensive device. As I said, it's very well accepted. The Schweitzer products are generally already used in substations and by the utilities. They know what they are and they're reliable. Also, the support network for the Schweitzer products and the Artac are excellent. So whenever we've had a question on how we would implement a function or what this instruction means, the folks over at Schweitz are very responsive to inquiries. They're more than happy to help support their product. So in summary, adding controls to the overall project cost of a solar site is very small adder. It is a little bit more money, but the controls themselves are very inexpensive, and the application of just reading a meter, taking a command and distributing the commands to the devices at the site, the application itself is very easy, very straightforward. So in addition to the capabilities to do active power curtailment and ramp rate control, you have the added benefit of being able to support voltage if the utility that you're tied in with wants to do some kind of voltage or power factor support. And we have a utility that we're working with now on defining how they would send us a power factor signal from their substation, and we would adjust the plant's power factor output to help them minimize the penalties they pay when they're buying power outside of the standard power factor range that they're supposed to be operating in. The Artac, it talks Modbus, it talks DNP3, it talks its own protocol, it talks the Goose protocol. So any of the standard protocols for devices that exist in the solar power plant, the Artac is capable of communicating with, so it's compatible with all the types of hardware that we run into. And it gives you some integration options down the line, like I mentioned, automatic generation control, power factor control, and has some capabilities built in to interface with other external systems. And lastly, having a system that responds a little more slowly and is less disruptive to the grid just allows the site to play friendlier with the neighbors. So that's it for our presentation. Hope you enjoyed it. Hope you got something out of it. My contact information is on the screen, and I would love to have some follow-up conversation if there's anything in there that you'd like to chat more about. Thanks.